Good day, ladies and gentlemen. I would like to begin this study session in the name of God, the most gracious, the most merciful. Today, we'll be looking at study session 2. Specifically, we'll be looking at Markov Analysis, which is study session 2 of BOS 312, titled Analysis for Business Decision 2, which also happens to be the continuation of the first semester Analysis for Business Decision 1. The session outline encapsulates the following. We'll try to understand the definition of Markov analysis, the assumption governing or surrounding Markov analysis. Then we'll try to look at various applications of Markov analysis. Then we'll look at the properties of Markov analysis. By implication, we'll look at the states and states probabilities. Then we'll move into developing matrix of transition probabilities, which eventually will lead to predicting the futures. These are the facilitators' information profile. But let's go straight into the subject matter. Markov analysis is named after a Russian mathematician named Andrei A. Markov. Markov analysis is a method used to forecast the value of a variable that is predicted or whose predictive value is influenced by only the attribute in the current state. That is to say, we use what is available currently and in the past to forecast or to predict, to anticipate what will happen in future. Then what we have on the screen are the assumptions underlying Markov analysis. Notable among the assumptions are as follows. There are limited or finite numbers of possible states. That is one. Two, the probability of changing states remain the same over a period of time. By implication, the probability of transitioning from one state to another stage, let's say state 1 to state 2, remain the same, remain constant over a period of time. Then, I believe that as soon as you consult your study material, you will see all these assumptions which you can digest independently on your own at your spare time. Then we'll look at the application of Markov analysis. There are several applications of Markov analysis in field of management. Specifically, Markov analysis has been employed by marketers in predicting market share analysis. It has been employed by financial analysts as well as accountants in monitoring rate of bad debt. Even currently, University of Abuja is employing Markov analysis in predicting the rate of student enrollment. We can also use Markov analysis to determine whether a machine will break down in future among many others. So there are many applications of Markov analysis. The list provided here is not exhaustive. Then what are the probabilities of Markov analysis? When we say states, state denotes possible condition of a process of a system. It is either a computer is functioning or not functioning. State 1 is functioning, so by implication, state 2 is what? Not functioning. If there are 3 suya spots in Gwagwalada, for instance, customer can only shop at one of these suya spots at a time. Then another fundamental property of Markov analysis is what we call the principle of collective exhaustiveness and mutually exclusive. When we say something is collectively exhaustive, it means that we can list all the possible states of a system or a process. That is, Markov analysis assumes that there are finite number of states of any system, which we've explained earlier. Secondly, the mutual exclusivity means that a system can only be in one state at a time. We have explained it also earlier. Then let's begin to look at the mathematical implication of Markov analysis. What is projected to you on the screen, P1 is state of probability for a period of 1. By implication, probability for any state can be probability for state of 1, state of 2, state of 3 to any state of nature. And what we have on the screen also is explained for user to understand. If you look at what we have in this slide, we give you an instance. For example, if we are investigating only customer, we may know that at this point in time, customer buys from a particular suya spot. Then the vector of the states can be represented as follows. P bracket 1 is equals to 1, 0, then close bracket. The P1 represents the vector of state of a customer in period 1, while P1 is the probability of the beginning of the first state, while P0 is probability of the period of the second state. Let's look at a particular example how we can develop transitional matrix moving from one state to the other. If we look at what we have here, the probability P1 is telling us that this is probability of 1 in state 1, probability of state 1 in state 2, probability of state 1 in state 3, among many others. Let's look at examples that typically illustrate this principle I've been trying to explain. If you look at this example, the status of customer visiting 3 supermarkets in Abuja at 2 points in time is shown as follows. The supermarkets are these respectively: Nest, ShopRite, and Sahaj Store. And these are the January numbers of customer for each respective supermarket. These are the February number of customer for the second respective supermarket. Then, in addition to the numbers of customer given above, the market survey yield the actual gain and losses for each of the supermarket. By implication, Nest keep 3,000 of its customer, lose 1,000 to ShopRite, and lose another 1,000 to Sahaj Store. If you look at ShopRite, ShopRite lose 800 to Nest, keep its customer 5,600, and it losses 1,600 respectively. Then let's see how we can use this information to solve a typical problem. From that question given, especially from the gain and losses, we total all the row. For Nest, 3,000 plus 1,000 plus 1,000 will give us 5,000. Then to get the probability, transition probability, then would you do 3,000 divided by the row total, which happens to be 6,000. And that will give us what we have in the Nest table. So as can be seen, these are the respective totals that we derive. These are the respective probability transition matrix that we derive by dividing each element in the row by the row totals. Now, this solution you see represent the current state probability transition matrix. Then we can use that same probability to predict the future states. If you want to look for the state, that is for the state of January, if you want to look for the state of February or March, we multiply the probability by itself, as we can see what we have there. But before we go into predicting the future states, let's understand the implication of what we calculated earlier in line with the transition probability that we derived. If you look at the solution on the screen, the transition probability matrix can be derived by dividing each of the elements in each row by the corresponding row totals, which we got this. Then what is the implication? If you look critically, Nest, if you look column wise, it has 6.1.1. Now, if you come to this table here, the probability of Nest is 0.6.1.1. Is being used to multiply the initial table we have here, this initial table here for January, 500, 800, 7, 5,000, 8,000, 7,000. If you observe this particular, you can see what we have here. The value is being used to multiply respectively. Then what do we have? We multiply 3,000 by 0.6. We have this. We multiply 8,000 by 10. 8,000 by 0.1, 7,000 by 0.1. Then we have all these respectively. If we sum everything together, it gives us 4,500. And if we divide it by the total, it gives us 22.5%. The same thing is done for ShopRite here by using the transition probability matrix to multiply the value we have. You can see it's titled February gain and loss. And if you notice here, we are only using what we have in February alone. What we have in February alone is what we have been using. Then here we have. The same is done for Sahaj Store. And if you can see, the market share respectively for Nest is 22.5, for ShopRite is 36.5, while for Sahaj Store is 41%. If you sum everything together, it has to give us 100. That is a checker for students to understand that what is being solved is agreeing with common sense convention. Then, this question also requires us to predict for March. Since this is February gains and loss, how do we predict for March? We simply go back to this table. Then we pick, we sum it up where it sum up to 1. If you look at 0.6, 0.2, 0.2, that sum up to 1. That is for next. 0.6, 0.2, 0.2. Now, these three metrics we have here is used for multiplication. You can see your 0.6, 0.2, 0.2. I would like to, let me use the board and illustrate this for proper understanding. If you observe critically what we have there, next, what we have there, for next, there are 3, 0.6, 0.2, 0.2 that sum to 1. The next has 3, this has 3, this has 3. If we go back to the table itself, that is the transition probability matrix that we derived. If we go back to this table, you can see next is 0.6, 0.2, 0.2, which is what we have here. So next will multiply itself, which is 0.6, 0.6, 0.2. In the same fashion, next will now multiply ShopRite, 0.1, 0.7, 0.2, which is 0.1, 0.7, 0.2. Similarly, it will multiply Sahad Store, which is 0.1, 0.1, 0.8. 0.1, 0.1, 0.8. Forming this, student will understand. Let me use N to represent nests. Let me use S to represent ShopRite. And let me use SH to represent Sahad Store. 0.6 times 0.6 is 0.36. 0.6 times 0.6 is 0.36. 0.6 times 0.2 is 0.12. Similarly, 0.2 times 0.2 is 0.04. 0.2 times is 0.2 times 0.2 is 0.40. 0.2 times 0.1 is 0.02. 0.2 times 0.2 is 0.40. In the same reasoning, this is 0.40. This is 0.02, 0.02. This should be 0.8. Then this should be 0.16. Totaling this will give us the probability transition of each. This is just to allow my student to understand how this table on this screen is being derived. You can see it tallies with what we have. If you total everything here, we have 0.4. If you total everything there, we have 0.28. If you total everything there, we have 0.32. If you sum this, it will give us 1. If it doesn't give us 1, the computation is wrong. Similarly, what we have here, we have computed for next. Then we need to go and compute for Sahad Store, which is the middle one. And if you want to understand how we compute for Sahad Store, let's simply go back to the initial transition probability matrix table, which is on the screen. Sahad Store is 0.1, 0.7, 0.2. So here will become Sahad. So here becomes 0.1, 0.1. Here becomes what? 0.8. It will now multiply the same set of everything. It will multiply next first, which is 0.6, 0.6, 0.2, 0.2. Here should be 0.2. Mistake, please. Then it will multiply itself, which is 0.1, 0.7, 0.2. Then it will multiply that of Sahad Store, which is 0.1, 0.1, 0.8. Since we are doing for Sahad Store, it will be 0.1, 0.7, then 0.2 for Sahad Store. Multiplying this by this, everything we have here entirely will change. I'm just trying to illustrate how we derive what we have on the board. Let me take you to the solution for easy understanding. This is for ShopRite. And as you can see, this times this is 0.06. And if you check what we have on the screen, that's exactly how we got the 0.06. This times this is 0.02. This times this is 0.02. Checking what we have on the screen is exactly how we got those figures. Similarly, 0.7 times this is what? 0.07. This times this 0.49. This times this 0.14, which is in tandem with what we have on the board. Similarly, we multiply this by this to get what we have on the board, which is 0.2. We multiply this by this. And when we sum everything, it results in a new figure, as we have on the screen, which is 0.15, which is 0.53, which is 0.32. Summing the three will eventually give us a total of 1, because the answer can exceed 1. Then finally, the final one we derive is the Sahat store. To derive the Sahat store, similarly again, everything will change, just in line with what we have on the board. And what we have on the board, we simply pick that of Sahat store, which is 0.1, 0.1, 0.8, which is not far different from what we have. And if we multiply everything, what we'll be having totally when we sum is 0.15, 0.17, 0.68. We simply multiply 0.1 by 0.6, we have 0.6, 0.1 times 2, together 0.1 times 2, 0.2. When we sum everything in this same fashion, we have what we have that is projected on the screen. Now, I want the student to understand, if you look at this next table, it looks strange. Next, column-wise is 0.40, 0.28, 0.32. Put that in your head for a while. 0.40, 0.28, 0.32. Then let's go back to what we calculate under next. Look at the column total here. 0.4, 0.28, 0.32. Then come back again and see. Is it not the same? We replicated row-wise. 0.40, 0.28, 0.32. The same thing is applicable to ShopRite. Let me take it back to that of ShopRite. You can see 0.15, 0.53, 0.32. Exactly the same thing is reproduced row-wise in this table. 0.15, 0.53, 0.32. Similarly, you can see the last, which is Sahat store. 0.15, 0.17, 0.68. These are sum total of various transition probability matrices that is being multiplied together. Then what do we have? We have 15, 17, and 68. All is 0.0.0. So this is the 2-period transition probability matrix. That is from February, it transitioned to March. These also can be used to find the proportion of the number of customers gained and the number of customers lost by each, which is what we are trying to see. If you look at this next slide, we say we cannot use the above 2-period transition matrix to compute for their respective gains and losses, which is what we illustrate here. For next, if you observe, we are simply using its transition probability matrix. Let me go back again for you to understand. What is the transition probability matrix? For next, what is the transition probability matrix? 40, 15, 15. This same thing is being used to multiply what we have here. And what we have here is simple. When we begin to multiply, it results in what we have in the next table. You can see the market share has begun to fluctuate. We have 21.25 here, we have 34.15 here, and we have 44.6. For you to properly understand how Markov analysis, the transition works, you need to refer back to our review of matrix algebra. This also can be derived using matrix algebra. That is why I said in the next slide we'll be looking at how matrix can be used to derive that. That is why we say alternatively the matrix algebra can be deployed to determine the next period transition probability matrix. For instance, this is the initial transition matrix that we derived earlier enough without being transitioned. This is for February, and we want to use this to transition to March. It means that we simply use this matrix to multiply itself, which is what we'll be seeing in our next slide. The February gain and losses, you can see the market share given here is being used to multiply this. We have the same market share we derived when we use the tree method. Similarly also, the March gain and losses. To get the March gain, we need to pick the transition probability matrix for February and use that same transition probability matrix to multiply itself. And that results in a new matrix. And this new matrix that you see is the same if you watch this new matrix that we see, column wise 0.40, 0.15, 0.15 is the same with this matrix that we derive. Is the same with this matrix that we derive using the tree method. So if you can alternatively use matrix to multiply, matrix algebra to multiply the matrix coefficient given by itself, or you use the tree method, you are still going to arrive at the same solution as seen by what we projected on the slide. Similarly also, the results of the transition matrix for match is being used to multiply the market share available. That result in a new market share, which we have to 0.2125, which is equivalent to 21.25%. Then we have 0.315, which is the same as 34.15%. Then we have 0.4060, which is the same as 44.60%. This is just using another methodology, which is the matrix algebra, to solve what we had solved earlier. That is probability transition. That is for probability transition matrix. Then the last part of this study session is the steady state equilibrium condition. What do we mean by steady state equilibrium condition? A condition that the probabilities transition matrix will become equalized in such a way that the transition will no longer be changing. It will become constant and the same. It will attain the state of equilibrium. This is a proposition put forward by Markov itself and Markov itself, that as soon as you continue multiplying the steady state condition, it will get to a stage that it will be giving you a constant steady state transition matrix. That is to say, it will reach the state of equilibrium probabilities. And in order to arrive at that quickly without multiplying, not knowing the number of transitions that we may compute before we get to that stage, mathematicians have developed, as well as statisticians, they've developed a methodology that we can use. Let's say, look at this identity given on the screen there. P equals, small p equals to capital letter P bracket multiplying by small p. While the capital letter P represent the transition probability matrix, while the small p represent the variables that will be used to multiply. Assuming that P is equals to A, B, C, D matrix given. Using matrix multiplication, if you multiply this matrix P with the small p, it will give us a new matrix entirely. And that gives this following set of equations, which we can employ our knowledge of algebra of simultaneous equation to solve. We can adopt a similar principle to solve 3 by 3 transition probability matrix for anyone that is having 3 by 3 matrix. Let's look at a typical illustration. In this example, suppose two products, Bua Cement and Dangote Cement, currently have market share of 40 and 60% respectively. Each month, branch switching take place among their customers. Of these two, of those who bought Bua Cement, 80% buy it again, while 20% switch to Dangote. Of those who bought Dangote Cement last month, 70% buy it again, while 30% switch it again. You can see for Bua, we have 80-20. For Dangote, we have 70-30. They now say find the steady state probability. That is to say, find the probability that for these two companies, their transition probability will be constant. Let's look at what we have. The first in the matrix P given there, 0.7, 0.2 is for Bua. 0.3, 0.3, 0.2, 0.8, not 0.3, 0.2, 0.8 represent Dangote. Then multiplying both. Let me use the ball to illustrate what we are trying to say. For Bua, we have 0.7, 0.2. For Dangote, we have 0.3. For Bua, we have 0.7, 0.2. For Bua, we have 0.3 and 0.8. And we agree that P1 for state of nature, P2 for the second state of nature equals to this multiplied by P1, P2. Remember our matrix identity, which we agree that the capital P is multiplying the small p, whereas also this is also the small p. Multiplying this, what do we have? We have 0.7 P1, 0.3 P1, 0.2 P1, 0.8, sorry, P2 P2 equals to P1, P2. Converting this to an equation, it will be P1 equals to 0.7 P1 plus 0.2 P2. P2 equals to 0.3 P1 plus 0.8 P2. And if you remember vividly, based on what we have on the board, if you remember vividly, this following matrix is being transmutated, being converted to linear simultaneous equation. But if you remember that both P1 plus P2 must equals to 1, this implies that P1 equals to 1 minus what? P2. So we simply pick in any of the equation, we substitute for P1, and substituting for P1 helps us to eliminate that again so that we can easily get our P2. So let's assume that in this equation, let's pick equation 2, that this is P1. So in equation 2, P2 equals to 0.3. Then what is P1? We substitute 1 minus P2 plus, are we together, class? 0.8 P2. Eventually, we have P2, 0.3 when we open the bracket, minus 0.3 P2 plus 0.8 P2. Collecting the like terms entirely, we'll have P2 plus 0.3 P2 minus 0.8 P2 equals to 3. What we have eventually here, we'll have, this is minus becoming plus, minus 8 here. This will be 1.3 minus 8. That will give me, sorry, this is 0.3, please. This is 0.3. If we operationalized everything, it will give me 5 P2 equals to 0.3. Then if we solve mathematically, what we will be having eventually, as you can see, will be 0.06, as can be seen on the screen. But let's complete what we are doing. Then eventually P2 equals to 0.3 divided by 0.5, which is equals to 0.6. But if you remember, P1 equals to 1 minus P2, meaning by implication, P1 will be what? 0.4. And that is exactly what we illustrate on the board. P1 is 0.4. So this implies that the steady state probabilities are for Boer cement, for their probability to be constant for every state, Boer cement has to be 60%, while Dangote cement has to be what? 40%. Similarly, we can extend this to 3x3 equation. Let me just glance through it in this our next example. You can see the matrix given in tabular form. We convert it into matrix form and apply the same principle. And we have 3 sets of simultaneous equations, which gives the following. P1 equals to the following, P2 equals to the following, P3 equals to the following. Similarly, as we arrived at this conversion that P1 plus P2 equals to 1 here, in the same reasoning, here, P1 plus P2 plus 3 equals to 1. So what is P1? P1 is 1 minus P2 minus P3. We substitute also the same way we substituted earlier when we are solving the 2 by 2. Eventually, what will we have? We have the following equation, which we have equation 4 and equation 5. And if we look critically, the equation 5 seems to be easy. We simply divide both sides by coefficient of P2 to obtain what is P2 in equation 5. Then we begin to substitute eventually. Then we begin to have 0.13, 0.13, 0.13 respectively. By implication, the steady state probability for Nest, for ShopRite and Actor are basically 33 1/3%, 33 1/3%, 33 1/3%. When we sum everything, it will coalesce into what? 1. This is what we've learned so far. we'll be able to learn the concept of Markov analysis and its various applications. We began by looking at the steady states. We began by looking at the what? The steady states. When we look at the steady state, we look at the transition probability matrix, and we can see how these can be applied on the surface level at this stage. I want my students to understand that when they get to final year, they are going to take another course, which this is prerequisite of it, which is production management, where we'll go into deeper application of Markov analysis. Thank you and God bless.